Hello Matrix, welcome to yet another video, and today we are going to be looking at paper 2 for your term 2 exams. Alright, so let's hope what we can do here will be enough to give you, the direction towards that exam. And then of course it will also help those who are doing their upgrades in this May-June. Okay. Of course, I've taken another paper from Mpumalanga from 2021. Don't worry about where the paper is from. Let's just look at what is inside and see if it can give us some skills to go through any particular exam. Of course, I've highlighted some of the most important instructions to make sure you understood before you begin the paper. And then don't forget that local instructions also take precedence over general instructions, so they are not to be ignored. Now, we are told exactly that you are to select an answer like that, and that's how we go about it. So let's go on. Now we are told here, the correct IUPAC name of the compound with the structural formula shown below is... Now, all you see here is hydrogens and carbons and something special. There's a bromine atom over there, or it's a bromide ion, if you will. So for me, this becomes a haloalkane, okay? And of course, for me, this is a functional group. Okay? Of course, you guys are told only to regard it as just a side branch. I don't know why. Because it perfectly fits a definition for a functional group. And in my opinion, the functional group is to be prioritized over everything else. But yeah, remember, whatever your teachers tell you, you stick with it even if it doesn't make sense, like this one right here. Let's have a look. What is the longest chain here? Let's look at this one from here. 1, 2, 3, 4, 5, 6. And then if we come from the side, 1, 2, 3, 4, 5. So obviously the longest chain is 6. What you call? It's 6 carbons. So that is our longest chain. So these are some of the things you want to do quickly. And then the question comes, from which side do we start numbering? Of course, for me, you only prioritize the functional group. So you want the closest distance to the functional group. So that would be on the 2nd carbon if we're coming from this end. And that would be on the 5th carbon if we're coming from that end. So already this is saying this must be carbon 1 and then that must be carbon 6. Okay? Great. And then we've got our methyl group right here. So this methyl group is on which carbon? If this is the 1st carbon, this is the 4th carbon. Alright? But like I said, you are told to regard this as a side branch. So again, you always want to have the shortest distance to the very first side branch. Now if you're coming from this end, the methyl group is on the 3rd carbon, compared to coming from the other end where the bromine atom is on the 2nd carbon. So in any case, you still will start on this side. So this becomes 2-bromo 4-methyl hexane. And that's the name. So at the end of the day, you've got an answer there. Investigate why the others are wrong. I really am not interested in telling you quite a lot, because sometimes they always try to create some of the most common mistakes that students make. So that is why the others are wrong. Okay, so the most common mistakes by pupils are exactly what makes these others wrong, because that is exactly what sometimes happens. Okay, next question says, which one of the following formulae represents an aldehyde? Okay, what do we know about an aldehyde? Well, we have a functional group. If you see something like a CHO, if we write it in a molecular formula, but in structural formula it's basically C double bond O, which is the carbonyl group that is bonded to a hydrogen and another carbon. So this means there's only one oxygen. Now you can already see here that we've got two oxygens here, we've got two oxygens here. So already these two are eliminated. Now these ones that only have one oxygen are the candidates. But what else do we need? We know that the general formula is going to be that of alkenes, CnH2n plus the oxygen. And then now all we have to find is this guy. Which of the compounds fits that of alkenes for the hydrocarbon end? Look, C4H8 is already doing it with an oxygen, so that should be the answer. And this one is saying this is basically CnH2n plus 2. Okay, so that's already something else, is it not? Yeah, so we're not gonna go with this one. It doesn't make that much of a sense, most likely an alcohol or so, but let's leave it for now. So the answer is B. Okay, so make sure you know enough to be able to make a decision. Now, in which one of the following options are the four compounds arranged in order of decreasing boiling points? So this means we are starting from the highest, okay, to the least, to the lowest. Okay, so how do we know this? Okay, let's look at what we have here. We've got an alkane because it's CH3 with the CH2 on the inside. So this is an alkane, a hydrocarbon. And then we've got a CHO here. That makes this an aldehyde, okay, of the same chain length. And then what we've got here, we've got an OH, which makes it an alcohol. All right, and then again for the same chain length. And then this one has that COOH, the carboxyl group, and of course for a similar chain length. So we've got an alkane, we've got an aldehyde, we've got an alcohol and a carboxylic acid. Obviously, for the same chain length, the carboxylic acid comes first. Okay, the next one is going to be an alcohol. Yes, the next one is going to be the aldehyde. Remember, the carboxylic acid has two sides for hydrogen bonding. That's what makes it superior to a primary alcohol, which only has one side for hydrogen bonding. This one has dipole-dipole forces, which are greater than the London forces, which are the only predominant forces in our alkanes, or should we say hydrocarbons. So C is ticking all the boxes, it becomes the answer. Obviously, you can't start with an aldehyde, you can't start with a hydrocarbon. Yes, this is a good start, but you cannot follow with an aldehyde and leave out an alcohol. All right, so that is why those other options don't work. Now we're told here, refer to the flow diagram, but1-ene. Okay, but1-ene, it's an alkene, so meaning there's a double bond on the first carbon. So let's try and look at it in terms of the structural formula. So we may have one hydrogen here, there's two here. So at times you need to be able to think quick. I mean, you've done this in term 1, so it should be second nature right now. Now, what are we doing to this alkene? We are adding hydrogen chloride, basically HCl. And what is that? It's a hydrogen halide, Okay. Now, if we are doing an addition because this is an unsaturated hydrocarbon. So in essence, we're doing an addition reaction. Okay, so with an addition reaction, we know that we are going to be looking at Markovnikov's rule. Okay, so Markovnikov's rule says you're looking at the two carbons that participate in the double bond. Okay, of course, that's the essence of it. The way it's defined in the book can be a little bit confusing. But if you're looking at the two carbons that participate in that double bond, when we break the double bond, what happens? The carbon that bears the most of the hydrogens will take the extra hydrogen, all right? And then the carbon that essentially has the less hydrogen will take the halide. That's Markovnikov's rule. So in essence, we're going to end up with something like this, CH3. What are you doing? With the CH, and then we're going to have the chloride atom here. All right, so this is something that we're going to end up with. And then that is essentially compound A. So what is that? That is 2-chlorobutane. 2-chlorobutane. So it says the main, okay, it says now the name of the main product, A, as well as the type of the reaction taking place. Already identified, it's an addition reaction. But for me, I prefer to say the name if they are looking for a name, because the type is an addition reaction, but the name then would be a hydrohalogenation. So it's not just a halogenation. There's a hydrogen there as well. And then we've already ascertained that this is 2-chlorobutane. So which one ticks all the boxes is option B. All right, so these ones are already wrong. Okay, so let's move on. 1.5 says the following polymer. Okay, I don't know if you guys are still doing these ones. Okay, maybe let's just highlight it instead. Okay, the following polymer is the result of the addition polymerization. Okay, so now we need to find the monomer. What would be the monomer? Let's see how many carbons there are here. 1, 2, 3, 4, 5, 6. So it's an even number, so we can actually divide it into 3 carbons, or we can divide it into 2 carbons. So what will guide this thing is the repetition of a particular pattern. As you can see here, if we're looking at 2 carbons, for example, if we're saying the monomeric form has 2 carbons, what do we notice about these 2 carbons? There's a chlorine and 3 hydrogens. Okay, just a moment. Okay, let's carry on. So you can see here, there is a chlorine and 3 hydrogens for a set of 2. And this thing repeats itself right here. This thing is repeating itself. So every time something repeats itself almost in the same measure, this is a sign that most likely the monomeric form is a 2-carbon, 3 hydrogen, and 1 chlorine. Okay, so let's have a look at it. The question says now, which one of the following is the monomer? Okay, the monomer is the smallest unit of a particular chain or a particular molecule. Of the above mentioned polymer, we can already see it has 2 carbons because there's repeats. Okay, so now that makes our lives a lot more easier, because how are we going to deal with this is this way. How do we name this? This is basically chloroethane. Yeah? Chloroethane, because no matter where you place this chloride atom, it will just remain chloroethane. It's already on carbon 1. So this is chloroethane. So that is it. So that's the story. Nothing great in there about that question. So the next question says, the reaction for a saturated salt solution. It is saturated in that you will not dissolve any more solute in this volume, okay? So technically, if you add more salt, it just stays suspended, okay? Either to the bottom or to the top, depending on the densities involved, but you cannot dissolve the salt anymore, meaning it won't disappear into a homogeneous solution. Okay, great. So we'll end up with a heterogeneous solution or a heterogeneous mixture. Great stuff. Now what is the question here? It says we've got sodium chloride, which is table salt. Going forward, again, once we see a double arrow like that, it means this is in equilibrium. All right. So it's going to form those sodium ions and those chloride ions. Great. Now the question says, which one of the following changes will favor the reverse reaction? Now for us to favor the reverse reaction, it means we have to either increase the amount of sodium, okay, or the amount of chlorine, because that is how we can reverse this reaction, because we don't know about the delta H. So we won't be able to tell whether this is a, what is the story now? We can't say this is an exothermic reaction or an endothermic reaction whatsoever. Well, intuitively you would want to say that the forward reaction is endothermic. Or you want to say it's exothermic because you're breaking a bond. When you're breaking bonds, what happens? Technically, you expend energy. So most likely the forward reaction is actually exothermic. But let's not go there at the moment because, yay, it's a dangerous one to attempt to answer at this point. So let's stick with what we have. The least we can do here is to change the amount, because pressure cannot affect the system. Why? Because pressure only affects gases and there's no gas here. So it can be an issue of concentration or amount in terms of number of moles. But we don't know what temperature would do, at least for now. Now let's see if the options will make any sense. Which one of the following changes will favor the reverse reaction? Heat the solution. If you heat the solution, remember it decomposes this. So actually, the forward reaction is endothermic. Yeah, think about it. Once you add heat here, you're going to separate those two atoms in the sodium chloride. So technically, to go forward, you need heat, or at least heat will do it, okay? So it will decompose the sodium chloride. So yeah, in a way, delta H should be a plus, in a way, but that is not indicated, so don't go for it. But we know if we heat here, what is going to happen? The energy will separate the sodium from the chloride more than it would combine these two. All right, so it won't work. It favors the forward reaction. Increase the pressure. Now, pressure affects only gases, so it doesn't come into the play. Add concentrated hydrochloric acid. Well, HCl, we know that it's a strong acid. It dissociates into hydrogen atoms or ions and chloride ions. Okay, but now what do we notice here? What we notice is that this releases chloride ions, which we contain in our original setup. Okay, so this is the so-called common ion effect. And now it means if we add in concentrated hydrochloric acid, we are going to be increasing the concentration of the chloride ions. And if we increase the concentration of the chloride ions, according to Le Chatelier, that would be the disturbance in that system in equilibrium. Therefore, it will shift so as to cancel that effect. That would favor the reverse reaction. Most definitely, this is the answer. Now, bubble chlorine gas through the solution. The problem with chlorine gas, this is stable. It naturally occurs as a diatomic gas. So if you're bubbling it through there, it won't really take effect unless you add heat or some sort of like UV light that can separate the chlorines into chloride ions. Then it would start to have effect. But as a natural gas like that, it just won't work. So the best answer here is C. All right, not a problem. Let's move on. Consider the chemical reaction represented by the equation below. We've got magnesium, so this is a metal. So remember from grade 10, when you react a metal and an acid, what happens? You produce a salt and hydrogen gas. And in fact, this is essentially the main guy for this reaction, but of course it depends on what you're trying to achieve. Now let's again inspect this chemical equation. What is the oxidation number of magnesium? It's 0 because that is its natural state. But the hydrogen here is a 2 plus, whereas the chlorine here is a 2 minus because of that coefficient. Because of the coefficient of 2 there, it makes those 2 minus and 2 plus, okay? But now, what is the state of magnesium on the other end? Magnesium here has acquired a 2 plus because chlorine is doubled and we know that it is a minus, so there's a 2 minus here for the chlorine to balance that out. So can you see the oxidation state of magnesium is increasing from left to right? But what about chlorine? Chlorine remains a 2 minus. So chlorine is a spectator ion here. Okay. Now let's look at hydrogen. Hydrogen is a 2 plus, and this time it acquires a 0. So what does that do to the situation? It tells us that we have a decrease in the oxidation number. So where there's an increase on one substance and then there's a decrease on the other substance in terms of the oxidation numbers from left to right, we actually have a redox reaction. Okay, so be able to inspect these things and understand exactly what you're dealing with. Yes, it's nice to get the answers quick, but it is more important to understand what's going on. So this is not an acid-base reaction. It's a redox reaction. Sometimes you may be hit with that as the question at hand. So which one of the following changes will increase the rate of production of hydrogen gas? So basically we're trying to increase the rate of the reaction here. If we increase pressure, remember increased pressure will favor the reverse because on the reverse reaction we have no gas molecules, whereas on the forward reaction we've got actually hydrogen gas molecules. So pressure will try to decrease the gas molecules, meaning it will favor the reverse. So the answer is no. Increase the volume. Okay, volume never affects the reaction rate. Decrease the concentration of HCl. Now if we decrease the concentration of HCl, we would essentially decrease the rate of reaction. So that would not actually increase the rate of production. So it decreases the rate of reaction instead. Now if we increase temperature, most definitely we will increase the rate of the reaction. So basically this is easy reaction rate related questions. Now 1.8 says 3 catalysts. Okay, what is a catalyst? It is a substance that facilitates a particular reaction by lowering the activation energy without itself undergoing a change or taking part in that reaction, so to speak. Okay, so I used to separately increase the rate of a hypothetical reaction. In the diagram, E1, E2, and E3 represent the effect of each catalyst on the activation energy. So the activation energy here is E sub 0 there, okay? For the reaction, here we go. We can see here's the number of molecules. It's like the so-called Maxwell-Boltzmann equation. Okay, number of molecules on the y-axis, and then we've got the average kinetic energy on the x-axis. Okay, not a problem. So the question says, which one of the following is the activation energy for the reaction with the highest rate? Now let's inspect our diagram a bit. Look at E1, for example. It has the least, it drops the activation energy to E1. So this is like the most drop, okay? It drops it by far, and that means the reaction rate should be higher. Then it would be the case for E, because E is intermediate, and then of course E3 is actually the least drop from that E0, E sub 0. So now the one with the highest rate is going to be E1. So this is straightforward, E1. So you don't even need to inspect why the others are not the options. It's a pretty straightforward question. Now, if the concentration of sodium hydroxide, that is a strong base, right? Because of the hydroxide ion there. Okay, solution is 0.01 mole per decimeter cubed. So we've got the concentration, then the hydroxide ion concentration of the sodium hydroxide, and the pH value of the sodium hydroxide at 25 degrees Celsius will be. Great. Now let's have a look. What happens to sodium hydroxide? It dissociates into sodium plus ions plus the OH minus ions. So it's a 1-to-1. So meaning 1 mole of base gives us 1 mole of OH minus, because we know that this part is what takes part in the what we call the pH calculation. So in any case, from here, what do we know? If we want to determine the pH, we use the ionization constant of water at 25 degrees Celsius. That was the key right there. That was just trying to tell us that we're going to have to use that. So we know that the concentration of the hydrogen plus ions multiplied by the concentration of the hydroxide ions is a constant of 1 times 10 to the exponent minus 14. Okay, easy. Therefore, we know that the concentration of of the hydrogen ions is going to be 1 times 10 to the minus 14 divide. Now, what would be the concentration of the hydroxide ions? Remember, it's a 1-to-1 molar ratio, so it's going to be the same because the volume did not change. So this is going to be essentially 0.01. So let's find out what that is. So this is 1 times 10 to the minus 14 divided by 0.01. So I'm getting 1 times to the minus 12 mole per decimeter cubed, of course. Alright, so yeah, stuff is happening there. Now what do? We know that pH calculation is minus the log of the concentration of the hydrogen ions, which is minus the log of this thing, 10 to the minus 2, which is just going to be 12, okay? If you know your maths, but you can use your calculator there to sort yourself out. Incorrect substitution. Okay, there we go. Now we know that, well, the concentration of the hydroxide ions is going to be effectively that 0.01, and 0.01 is actually 10 to the minus 12. Okay, that's just what it is. Sorry, not 12 but 2. Sorry. Hey, what are you doing? Yeah, almost made a meal there. So the concentration there is 10 to the minus 2, because it is the same as the concentration of the sodium hydroxide. This one is actually the concentration of the hydrogen ion, so that is already eliminating those two options. Then the pH, we can see it's 12, but not 2. So which one ticks the boxes is C. Okay, great stuff. So that was a bit of a question that never allows you to just walk free. You've got to pay some dues somewhere. All right, if base X is titrated against acid Y, the pH of the solution is 9. So if the pH is 9, it means what happened? It already tells us that the base must be a strong base. And this one must be a weak acid. Okay, just remember the hydrolysis of salts. It comes from that theory. Because remember, a strong base, when reacted against a weak acid, because that weak acid dissociates incompletely, the strong base will take precedence. In any case, it produces what we call a basic salt. And the basic salt's pH will be greater than 7. Easy. So now it says, which one of the following combinations correctly represents base X and acid Y? Of course, anything that has a hydroxide in it is a strong base. Anything otherwise, those are weak bases, so it can't be a weak base. The acid cannot be a strong acid like nitric acid, but ethanoic acid definitely. It can't be sulfuric, it can't be HCl, because those are strong acids. So the answer is here going to be B. All right, not a problem, guys. Let me just take a moment and sort something out. I'll be back in just a few minutes so that we can carry on with this lovely paper. Okay, so question 2 says, consider the following 8 organic compounds represented by letters A to H. Okay, we can see propanone. It's it's a ketone basically. And then we've got C2H4. This follows the formula CnH2n. So that's an alkene. So we've got a primary alcohol here. And then on D, we've got a haloalkane. Again, this one is a bit more complicated, okay? Because there's a chloride atom, there is a bromide atom, and we've got a methyl group as well. So there's a lot to think about. So again, let's look at the longest chain. What would that be? 1, 2, 3, 4, 5, the straight one. And then if we come from this end, 1, 2, 3, 4, or 1, 2, 3, 4, so that can't be. Now let's bend it 1, 2, 3, 4, 5. So whether straight or bent, it has 5 carbons. So the most important is to make, if the straight chain is the longest chain, it's always safer to just use that. And then of course, this tells us we've got 2 methyl groups. In any case, we're going to come back here. Let's move on. And then here, we've got a CHO at the end. So you know what that is. That's an aldehyde. Okay. So we've got an aldehyde there. And then here, we've got the COOH, which tells us we've got a carboxylic acid. And then we've got a 2-methyl propane. That's just a branched alkane, okay? And then here we've got an ester. So we've got an ester there. Anyway, we are sorted. Let's just move on. It says now write down the letter that represents the following. Okay, now we're going to start working on this side. So we are answering so we're doing question 2 here. So we've got 2.1, and then it's divided into 2.1.1. So we want a weak monoprotic acid. So what do we know? It's going to be the COOH. It's a weak acid. That's ethanoic acid or acetic acid. So we want a letter, so that's letter F. Now let's look at 2.1.2, a chain isomer of, see what is happening here. If you've got, for example, a CH2 and it has a subscript, it means it is within that chain, okay? So you can already see that this is an alkane, essentially. If there's 3 carbons here, it's going to be 3 plus 1, 4, 5. So this is pentane. Okay, it has 5 carbons. So this becomes the isomer. Okay, it's a chain isomer because this chain is branched. So you've got 2 methyl groups and a propane. So that makes it a 5 carbon. So that becomes letter G. Okay, so 2.1.3 says a compound used as a reactant in the preparation of compound H. Now remember, compound H is made from a carboxylic acid as well as an alcohol. Now, what do we see? We see this propanol here. This is propanol, or you can call it propan-1-ol, okay? It's up to you, really. I mean, it's on the first carbon, so it's propanol or propan-1-ol. It's okay. Now, we can see here we've got ethanoic acid, but on this ester here, we've got what? 1, 2, 3. So this is propanoic acid. And we've got propanol here because this is a propyl group. So it's probably, we're going to use letter E here, because compound H is made from propanoic acid, and that is ethanoic acid. So it's essentially going to be compound C, because we can see there is a propyl group which comes from the alcohol. Okay, so we've got 2.2 to answer here. Now it says write down the structural formula of the functional group of compound A. Now compound A is a ketone. So ketones have this carbonyl group. Okay, so it's usually written like that. But in any case, yeah, man, leave it like this, leave it like this. I think that is fine, or even if you cut off those C's, it doesn't matter. That's just the carbonyl group, because compound A is essentially the carbonyl group. I don't know if I remember it well. So that's what we've got. Normally, we show that this carbonyl group is bonded to 2 other carbons. I think that is the key statement there, as opposed to aldehydes. Okay, now name the homologous series. Remember, homologous series is a group of compounds that can be described by the same general formula. Okay, so name the homologous series to which F belongs. F belongs to carboxylic acids. All right, and then 2.2.3 says the IUPAC name of compound H. Of course, we start with the propyl group. We start with the propyl group here, right? It's 3 carbons, so it's going to be propyl. No, that's not how we write propyl. Propyl propanoate. Okay, so it's propyl propanoate. I don't know why, man. I always manage to write badly somehow. Okay, propyl propanoate. Yes, because there's 3 versus 3 there. Okay, easy. Of course, you get the mark for each one of the two. 2.2.4 says the IUPAC name of compound D. Now that one is a problem. Okay, so that one is a problem. Now let's look at it. We've seen that the longest chain is 5 carbons, so that is a pentane at the end. But now we've got 2 halogens, and for me, a haloalkane, you always prioritize the functional group. So here you can decide which one do you get to the quickest. It's of course the chlorine versus the bromine. The bromine is on the 3rd carbon on either side, even if you're coming from the left end or the right end, it is on the 3rd carbon, so it doesn't become an issue. So the closest to as many side branches is essentially that chlorine because it's on the 2nd carbon. Now again, we're going to decide what about the methyl group. It's also on the 2nd carbon from this end. So now what do? We ask ourselves alphabetically, because now these ones are on positions that actually compel us to choose either side. Then we start to go alphabetically. So which one comes first? Methyl before chlorine, because remember, they want you to consider the halides, or should I say the halogen atoms there, as a side branch rather than a functional group, which is ridiculous, is it not? But anyway, let's leave the nonsense to them. They decided it, so we're just gonna go with it. Sometimes if you can't beat them, you join them, isn't it? Yeah. Now let's see. We can see that definitely the side of chlorine will actually become better off. Why? Because alphabetically chlorine will come before methyl, right? And then bromine is essentially halfway, so it doesn't become an issue. So this is carbon 1, that is carbon 5. Okay, so let's start. We know that our friend here is going to be 2-chloro. No, not 2-chloro. Remember, you name it alphabetically. B comes before C. So this is 3-bromo. Two chloro, and then this is going to be now 3,4. Dimethylhexane, pentane. So that's quite a name, right? So you can see here for each substituent, naming it properly, 2-bromo, 3-bromo, 2-chloro, 3,4 dimethyl pentane. Yeah, that one, they should have made it 4 marks actually, because the position of the dimethyl groups is also important on its own, and the parent chain, which is a pentane, is also important. So I don't know why they are deciding to just squeeze you guys there, because honestly that deserves a bit more marks. Okay, let's do 2.3. It says now compound C is a primary alcohol. We can already see that. Okay, so there it is. We saw that it is propan 1-ol or propanol. Now it says define the term primary alcohol. Okay, now that's fine. The primary alcohol, you can just say is is an alcohol molecule or compound that bears the functional group in brackets you can say the hydroxyl group on a primary carbon, which is a carbon that is bonded to only one other carbon. Look guys, there's no specific way that you can answer questions. So me, I am a person who likes to be flexible. You decide if you like it or you don't like it. You can claim this definition as it appears in any document that you can get your hands to. But what is important is an understanding from you. If you can express an idea in your own words, but still maintain the science, for me, you're a good student because it means the teaching became successful. But if you regurgitate, I'm not too sure whether you're just, going through the motions or you actually understand. But either way, it's not a big deal. So basically, it's an alcohol molecule that bears the functional group on a primary carbon. You can explain that it is a carbon that is bonded to one other carbon. However you want to put that, but please make sure you don't leave out important information when you write a definition, especially in your own words. Okay, write down the structural formula of the positional isomer of compound C. Now remember, we just want a positional isomer. Okay, not a problem. Actually, now I started doing my own things here. Let's do the right thing. Let's do the right thing. Okay, this is 2.3.1. Okay, so now we want to do 2.3.2. It says write down the structural formula of the positional isomer of compound C. Obviously, there's 3 carbons here. Now, the OH group was on the first carbon. So now it can only be on the second carbon if we like. Okay. In fact, that is the only other position it can be. Alright. So because if you put it on that other carbon, it is essentially the first carbon. So you can just decide to put it down below or up top. It's essentially up to you. So you're getting a mark for the parent chain and the position of the functional group. So now let's do 2.4. Okay. 2.4 says compound B is considered unsaturated. Yes, of course, we could see that it is an alkene. Yes. Now, if they start saying that, they would be wanting. Then it says, give a reason why compound B is unsaturated. It contains it has a double bond between 2 carbons. Yep. Okay, So basically it has a multiple bond. But to be specific, because they chose compound B, we know that it has a double bond, not bone. Yo, hey. Be careful of what you write, eh? Please read what you wrote. Don't write and think you wrote it well. You will find things you have not thought of in life. Anyway, again, I'm making the same mistake. Yo, doch. Why now all of a sudden I'm so erratic? So this is 2.4.1. So 2.4.2 says write down the name of a solution that you can use in the laboratory to test whether compound B is unsaturated. Write down the name of a solution that you can use in the laboratory to test whether compound B is saturated. You know that we use the iodine solution. Is it iodine or bromine water? Yeah, it's usually bromine water. Yeah, man. Bromine solution. Just say bromine water or bromine solution. Because they said name of the solution, we can use that. It helps us to understand what's going on. Okay, so then the next question, 2.4.3 says, what will be observed when this solution is added to compound B? It loses its color. We can just say it loses its brown color to colorless. Because we know that haloalkanes are colorless. Now it says write down the IUPAC name of the product formed. Great. This is 2.4.4. Now what would be the IUPAC name? Remember, we can see that that is ethene. We've got ethene here. And then we're going to add Br2. So what do we end up with? Well, technically here, we will have a situation where the bramines will just add on either. So it's going to be CH, Br, CH. Br, okay. No problem, because it's an addition reaction here. So what happens? We're going to get a 1,2 dibromo, right? So it's 1,2 dibromo ethane. Okay, easy stuff. Easy stuff. So that's the most important. That's the most important. Again, you're getting your 2 marks. So that is how you score those 21 marks. Again, this is a very common question, guys. Easy, 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 easy. I have no idea how I ended up like that, but I did anyway. So let's go on. Question 2. I don't know how I jumped. No, not question 2, but question 3. Now, what do we get here? It says now an experiment is conducted to determine the boiling point of organic compounds. So, what is the purpose? It is to determine the boiling points of organic compounds from different homologous series. All right, under the same conditions. Great. So we can see here compound P is hexane, it's an alkane. And then we've got compound Q, which is 2,3 dimethylbutane, essentially a 6-carbon compound. So which means it's an isomer, it's a chain isomer of compound Q. And then we've got a methyl propanoate, so this is an ester. Okay, not a problem. And then we've got pentane 1-ol. Okay, great. So that is fine. But now what we notice is that methyl, let me check, no, methyl propanoate has nothing to do with pentane 1-ol. So there's not so much of a relationship. They are not even chain isomers. But the first two, we can see that these are chain isomers, but the last two have no relations per se. Okay, now it says consider the following boiling points of compound P to S given in random order below and use them where applicable to answer the questions that follow. Great. Now we're going to start 3.1. It says write down the independent variable for this experiment. So what seems to be changing here? It's the functional group, is it not? That is what is independent. As we change the functional group, we expect to see a change in a change in the boiling point. So this is the functional group, or you can say homologous series. So let's just say the independent one is the functional group. It's okay, because the physical properties are actually imparted by the functional group as compared to just, other things. So it is the functional group, or you can say homologous series if you will. Okay, 3.1.2 says write down the structural formula of compound R. So methyl propanoate is basically, this is the story like this. Okay. However you orientate this organic molecule, as long as you have the methyl group facing the oxygen, and you've got that 3-carbon which bears the what you would call a carbonyl group, but it's not. Okay, it's just basically a carboxylate group because it goes together with that other oxygen. Anyway, that is the structural formula of compound R, methyl propanoate. See here, there's C4, so there's 1, 2, 3, 4. There's 8 hydrogens, 3, 5 plus 3, 8, and then 2 oxygens. So you see it balances nicely. So please make a habit of double checking if things are in order. So 3.1.3 says the boiling point of compound R. Now let's have a look. Which one will have the highest boiling point here? It's basically going to be an alcohol. So this should be S, right? And then the next one, it's going to be the one that has dipole forces, which is the methyl propanoate. So this should be R. And then what do we know? The next one, wait a minute, they didn't put them in any particular order. Okay, so the one with the highest boiling point, which is 138, should be S, actually, the alcohol. And then the one that follows the alcohol, which is going to be the 79, should be R. Okay, and then the one that follows 79, which is going to be 68, is going to be the straight alkane. And then the branched one will have the smaller boiling point. So this becomes Q. Okay, great. Sorry that I did not inspect that quickly. So it says now the boiling point of R should be the 79,8 degrees Celsius, because it is the second highest boiling point in this series of organic compounds. All right, 3.1.4, the boiling point of compound S, so it's 138,5 degrees Celsius. Not a problem. So it says now explain the difference in the boiling points between compound S and R. So this is one of those questions which are problematic. So what do we know about S and R? S has hydrogen bonds, whereas R has dipole-dipole forces in addition to the London forces that they contain. And that is why those two have differences in their boiling points. So we can just say compound R, or let's just start with S. Compound S has strong hydrogen bonds between its molecules in addition to weak London forces. All right, that's point number one. Number two, what I like to do though, I like to compare these things in one statement, and then would say more energy will be required to separate the molecules. To separate the molecules. Hence, a higher boiling point, not brewing. Okay, and then of course you can write stuff about compound R if you feel like you can, but I like to complex my arguments. I would say compound S has strong hydrogen bonds between its molecules in addition to weak London forces, compared to compound R, which has dipole-dipole forces in addition to London forces. I like to do that simultaneous comparison, but you can do it separately. You can just say this one has dipole forces between molecules in addition to weak London forces. You can just say all these are weaker than those in S. Okay, you can say lesser energy is required to separate its molecules than in S. And then we can say hence its lower boiling point than S. Okay, so you can just do your thing here, freestyle as much as you want. You can consider both or just one at a go. It's absolutely up to you how you want to attack this thing. But whatever you do, make sure you talk about intermolecular forces, because boiling point is linked to intermolecular forces, not intramolecular forces. Okay, now let's go for 3.3. It says now, the following graph shows the relationship between vapor pressure, you see, very common question, and temperature of compound P and Q. What did we say? Compound P and Q are actually chain isomers of one another. Of course, P having a higher boiling point than Q because Q is branched, assuming a more globular shape and a shorter distance for the action of intermolecular forces, leading to a lower boiling point for the same molecular mass. Okay, the dotted line indicates the external atmospheric pressure. Okay, not a problem. Now let's see. Remember, when vapor pressure is equal to the atmospheric pressure, it boils, is it not? Okay, not an issue. So it says now define the term vapor pressure. Again, it's a very common question. That, guys, you need no second invitation on this one, because if you don't know it, please kill yourself, because it means you're not going to school, you're just visiting there. So vapor pressure, we can just say, is a pressure exerted on the surface. Okay, the pressure exerted by the vapor on the surface. Okay, wait. It is a pressure exerted by the vapor on the surface of its fluid when vapor is in equilibrium with the fluid. Okay, so basically, there's ways to define this nicely. Sometimes I become a bit erratic because I sometimes overly exert my opinion, so it happens. But either way, if you are opinionated as I am, you are fine, just go for it. But make sure things like equilibrium come out somehow, okay, in a nice way. And there has to be the pressure that is exerted on a vapor. It's a pressure exerted by the vapor on the surface of its fluid when the vapor is in equilibrium with the fluid. Great. Let's move on. So we're going to do 3.3.2. It says now, using molecular formulae, write down the balanced equation for the complete combustion. So once you hear that word complete, maybe let's highlight it so that it's clear to you folks. Once you say complete, it means there's an excess of oxygen. So we have to use molecular formula for compound P. They've already given us the molecular formula for compound P, so it's C 6H14 plus oxygen. So that would be oxygen in excess. And that gives us carbon dioxide plus water vapor. Okay. Of course, this is a gas. This is also a gas. This is a gas. This is a liquid. Remember, anything that is more than 4 carbons in a chain is a liquid, most likely. Anyway, let's leave it at that. We don't care what it is, but it's a liquid. Now, what do we do here? We can see that, look, we've got 6 carbons, so we'll need 6 carbons on this side. So we can balance the carbons first. Then now that that is sorted, we can see we've got 14 hydrogens, but we've got 2 here, so we just add a coefficient there of 7. So that makes it 14. Now, the last thing to balance is oxygen always. So always do oxygen last. Now let's look at the oxygens. We've got here 7 oxygens plus 12. So that makes it 19 oxygens. So we can put 19 here. But now when we make 19, it's 19O2, it becomes 36, right? No, 38, sorry. So we have to divide this by 2 to make it exactly 19 oxygens on this side. But now we don't use a division by, look, we're using molar ratio, so you can't have half a mole. Okay, so the thing is, we multiply throughout by the common denominator, which is this guy. So we're going to end up with now 2 C6 H14 plus 19O2, giving us 12 CO2 plus 14 H2O. Okay, so let's see if everything is in order. And then of course this is liquid, this is gas, gas, gas. All right, now we've got how many? 12 carbons. We've got 12 carbons. We've got 28 hydrogens. We've got 28 hydrogens. We've got 38 oxygens there. And we've got, this is 12 by 2 is 24. 24 plus 14, that's 38. Okay, so we are sorted. Everything is balanced. So this is your answer. Of course, when you're answering this question, you only write the answer. Nobody cares how you got it. Okay, great stuff. So please, this is a very common question. You don't need to be getting it wrong. If you're getting it wrong, it means you are not paying attention. Okay, so let's move on. Now it says, which one of the compounds P or Q is represented by graph 2? So now look at graph 2. It has a lower vapor pressure than graph 1 for the same temperature. So these are some of the things, guys, you need. Skills of graph interpretation is stuff you do early in your grade 10s or so. So you need to be able to compare things. Look, for the same temperature, you can pick any point for that matter. So consistently, if you just pick these temperatures right here, I'm just going to overly do this thing so that you can follow. So now do you see, if we pick this temperature here and there, okay, let's just not do too many things. We pick this temperature there, and then that one, and then that one, and then that one. All right, so what do we notice, guys? We notice that for the same temperature, this one has a higher vapor pressure than the other. Okay, higher vapor pressure than the other, higher vapor pressure than the other, higher vapor pressure. Of course, this one is highest than the other, so maybe we can leave this last panel here. because it doesn't help us much. So clearly we can see that the vapor pressure of graph 1 is greater than the vapor pressure of graph 2 for the same temperature, because we measure vapor pressure for a given temperature. Now, which one has a higher vapor pressure than the other? Obviously, this one has a lower boiling point than this one, isn't it? Because the intermolecular forces on a straight chain are much stronger than on a globular structure like a branched alkane. So the lower the boiling point, the higher the vapor pressure. So now the question says, graph 2 represents which one? It represents P, because it is the one with the lower vapor pressure compared to the other for a given temperature. So it is compound P. So we've got 3.3.3, so this is compound P. We can just write P. It says now fully explain the answer. Again, it goes to what is going on here, intermolecular forces and why they are different. So these questions, guys, are easy, but you can see here it's a bit more tricky, because now you have to, use a graph and also your knowledge as well to be able to do your thing. So it's a bit more nicer and a bit more challenging than the standard stuff you are used to. So let's go for it. 3.3.4. We can say P is a straight chain hydrocarbon and Q is a branched chain hydrocarbon. Of the same molecular weight as P. Okay? You know. Now what do we know? We can say now the intermolecular forces in P. Okay, let's try to write properly. I don't know why it always does this. The intermolecular forces in P have a larger surface area for their action. Compared to Q, which has, a smaller surface area. Okay, we can say therefore the intermolecular forces, I'm tired of writing, guys, I'm gonna write it in full. The intermolecular forces of P are greater than those in Q. More energy more energy is required to separate molecules of P than those of Q. Therefore, Q will have a higher vapor pressure for a given temperature than P. Look, there's plenty of ways, guys. There's plenty of ways, guys. You can say this. I mean, I've said quite a mouthful because you're only getting 3 marks. So again, you look at the marks and decide how you're going to attack this. Here, I'm not leaving anything out because I like my points to be logically connected. Remember, don't think if you put 6 points like 1, 2, 3, 4, 5, maybe 6. Actually, you may get a half a mark for each point that you made. So it doesn't mean that when you put a bit of a paragraph, you know, you are doing too much. These for me are better because everything seems to be connected. Everything has to flow. Everything has to be systematic. All right, not a problem. So the question says now read draw graph 2 in your answer book. On the same set of axes, sketch the curve that will be obtained for compound S. Now remember, compound S is an alcohol, so it will have a lower vapor pressure. So I'm going to draw it right here. Let's just take out all of these things now so that we can put a nice graph. So this one will start the same, at least because nobody told us. But this one will be stuff like that. All right, so we can name it S. What did they tell us? Yeah, label the curve S. So this is S. Great. So basically, this simply says for the same temperature, it will have a lower vapor pressure than the other two. So I'm only drawing it there, but you are only expected to have this and that, and this one is not included. So you are not allowed to draw it there, but I'm doing it there because I can. Okay, not a problem. So we've got here 3.3.5. just say C graph. I've done it for you guys. So this is the easiest, no questions asked. Let's move on. Now, you're always going to have a question on organic reaction. So do you see, if you ignore work on question, what is this? On term 1. If you ignored any work on term 1, then it's going to hurt you when you have to look at it here, because trust me, these questions are not going to come back in the same level. They will try to create problems for you. Those are going to definitely give you a challenge. That is questions from term 1. You'll still have Newton's laws of motion in paper 1. You will have projectile motion, vertical projectile motion. You're going to have momentum. You are going to have, what is this? Yeah, what was there? Oops, doch, I forgot these things. But either way, work that was done on term 1, you need to know. And this time you need to know it in detail because it's going to be more challenging than the standard it normally is, okay? So be ready to sweat a bit. So my advice to you, go and watch all the videos I have done on term 1 so that you can get the feel, because I kind of mixed them up. I took questions from trial exams, took questions from some final exams, and put them there so that you have a bit of everything that you need of different levels of difficulty, so that you can just sail through your term 2 exams. Otherwise, they're going to hurt you. They are meant to hurt you anyway, so please don't get hurt. Now let's try and quickly do this one. This question says, consider the flow chart below. showing different organic reactions. Of course, guys, I think I did promise that I was gonna do a video on this, but I don't know. It doesn't look like it's going to happen, but I'll try. Okay, now consider that flow diagram and answer the following questions. Now, A to D are organic compounds, 1 to 6 are organic reactions. Now let's have a look here. What is going on here? We've got compound A, which is our starting point. Or so it seems, or so it seems. Let's just play with the colors a bit. I am loving these electronic thingies. I never thought I would, but yeah, I'm actually impressed. Now, we can see here this compound, we added a halogen. But this one is diatomic, right? Chlorine gas. But now the issue is that what is the story about this guy? Why do we need UV light? Remember, UV light, it's ultraviolet. That has high energy. So why do we want energy? Because we want this guy to split our friend into its halides, because the energy that it brings from its photons, when it delivers them onto these molecules, they will break into halides, the two chloride ions. So we're going to end up with a Cl minus and a Cl minus when that energy is dropped by that photon from UV light. Okay, you see a bit of photoelectric effect is coming back, because this is how we treat cancers, isn't it? Cancers use the treatment of cancers, the radiation therapy or radiotherapy actually uses photoelectric effect, because you have some isotope of some, metal or whatever. Then once you energize that thing, it decays, because those are radioactive, isn't it? They decay by emitting these photons. And now when they hit tissue, of course, you vary certain distances and angles so that you concentrate the energy at a particular space for a particular distance so that you don't damage other structures. But I'm just giving you the idea about organic chemistry. I mean, look, not just organic chemistry, but physical science in general. It has a strong application in medicine. If you're considering a career there, you will learn a lot, because then you will start to understand the technicalities of how those machines are produced and what exactly is the purpose. You can even give ideas to engineers thereof to now design machines that are going to be more efficient than the ones we currently have. And that means you may start to have a lot of money than just being a doctor. Because once you start designing, the equipments using your friends or colleagues who are engineers, then you guys together start making money instead of stealing money like you, the doctor, who's trending right now. It's embarrassing, but hey, people do anything for money. But please choose the right route. It's not always nice, because there's a lot of rip-off in the right route. But yeah, there's a lot of gains in the bad route, but when it backfires, everything collapses. So you don't want to be in that situation. Anyway, let's not talk too much. I was just moved by the use of UV light, because it essentially separates our halogen into its halide ions, basically, because of the photoelectric effect. When that light decays, it emits those photons. Anyway, let's move on. What do we end up with? Now we can see that, oh my lord, we've got a situation here. We've got 4 carbons. If we've got 4 carbons and all we added was just a halogen or a halide, technically it means this guy is also 4 carbons. But now we only have 1 halogen added. 1 halide atom of this halogen, or 1 halogen, whatever. We only have 1 instead of the 2. So what happened? It means the other one was ditched. So this dude here was incorporated into that molecule. And then the other one is just wandering. He's just wandering about and ready to be picked by whoever. So this already tells us we did a substitution reaction, because Here, clearly we had a butane, because there's 4 carbons. We had a butane, and as a result, because this one is more electronegative than hydrogen, it kind of kicked the hydrogen out. Of course, UV light does a bit of that job of giving enough energy to work on that bond as well. So technically, this guy is going to shed a hydrogen in this direction, and these two are eventually going to find each other and form a hydrogen chloride molecule. So that is what is going to happen with the other chlorine. And then of course the other chlorine is going to substitute that ejected hydrogen. So this guy gets fired and is replaced by a better candidate to form this haloalkane. So technically this is a substitution reaction. And this substitution is basically halogenation if you think about it. But anyway, let's leave it for now. The type is a substitution. We move on. Reaction 2, we're moving from this haloalkane to an alkene, because remember this C5 follows this formula CnH2n, meaning it becomes an alkene. So if it becomes an alkene, it means we eliminated. So reaction 2 is an elimination reaction. I'll just write elimin. So basically it's an elimination reaction. But I like to write in full. So reaction 2, basically it's an elimination reaction. So we eliminated, and you know that when we do an elimination, it means we're going to lose a chlorine and a hydrogen. So basically it's a dehydrohalogenation. And we know that we need here some strong base like sodium hydroxide. So please remember these things. This one is a strong concentrated base. This one must be concentrated, because if we don't use a concentrated, we'll start doing hydrolysis instead. Okay, it must be concentrated. Now reaction 3 says we're dancing back and forth. So if we're going back into that, so what would mean is that we have an addition reaction here, because from an alkene to a haloalkane, it means we did an addition reaction. And then of course here we'll have added a hydrogen halide. So this is a hydrohalogenation, double H. Okay, so that is the story that's going on in there. And then now we're going to go to reaction 4. Reaction 4, we're coming from some compound, main product, that came from reaction 6. But all we can see that we're moving into an alkene. All right. So if we're moving to an alkene, we're also doing an elimination reaction. Most likely, but we'll find out. And then let's see. This elimination reaction, obviously, we have done something here. We will find out, because we can't classify it as yet. We need to first consider reaction 6. What is reaction 6? Okay, guys, I'm taking longer than I wanted to, because I don't want in the next hour to be struggling with these questions still. Okay, let's move a bit quicker. So now we moved from this haloalkane in reaction 6. I'm just jumping ship because it's a bit of a problem. Okay, let's not jump ship. Let's go to reaction 5. Reaction 5, we're coming from this alkene to some major compound. But look at what we used. We used an acid. And we're using steam. So steam is basically H2O. Okay, so if we add water, so we're hydrating this thing. So it's an addition reaction. and it's basically hydration. Okay, meaning this phosphoric acid acts as a catalyst. Okay, great stuff. So it is just a catalyst, because what is going to act here is going to be the steam. Okay, not a problem. So if we're adding water, remember, this will impart the OH group. So this becomes an alcohol. Now we understand what that is. And if it is an alcohol and we're going to an alkene, it means we're doing a dehydration reaction. So this is a dehydration reaction. So do you see, sometimes you don't have enough information until you look elsewhere, and then you follow the flow diagram. Now that's great. Now let's have a look at this reaction 6. Now if we moved from a haloalkane to an alcohol, we are doing a substitution reaction. And this reaction is hydrolysis, basically. Okay, and here we use again sodium hydroxide, but this one is dilute. Okay, when you have a dilute strong base, you do a hydrolysis reaction, which is a substitution reaction. So now that we've worked through our flow diagram just right, let's quickly rush into these questions then. It says now compound A is a hydrocarbon. Okay, 4.1.1 says define the term hydrocarbon. We can just say a compound that only contains, or let's just say consists, of and hydrogen. Okay, so a compound that only consists of carbon and hydrogen, that's a hydrocarbon. Easy definition. Again, you don't be choking on these things, guys. If you do, please kill yourself or call me to kill you, because I can gladly. When you don't do your work, I'm very happy to take you down. Okay, but if you do your work, I will even consider giving you the benefit of the doubt. So write down the IUPAC name of compound A. Now we can see that compound A is basically a butane. That's what it is. It's 1, 2, 3, 4, 5. No. It's a pentane. Okay, mistakes there. So basically, this is a pentane. Yeah, because compound A is a hydrocarbon. So it's a pentane. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes. So it's a pentane. Easy stuff. Easy stuff. And then 4.2 says identify the type, okay, of reaction for each of the following. Okay, great. Remember, when they say type, you must decide whether this is an elimination versus substitution versus whatever. But now that is the story. So the type of reaction for each of the following. Reaction 1, we can see that we did a substitution reaction because we took a saturated compound into a transformed form of a saturated compound. So we must have substituted something by another. So 4.2.1, we know that this is a substitution reaction. And then of course you guys get allowed to start naming what type of a substitution reaction it was. Well, I do not like that. Let's leave it. Some can say it's a halogenation, but leave it alone. It's a substitution reaction. So when they ask you a general question, stay general. Don't be specific. They didn't say the specific name. Anyway, let's go on. Reaction 5, we discovered that it is an addition reaction. Again, you can name it that it is hydration because you're using steam, but they didn't ask you the specific name. They just said type. So that is general stuff. Okay, reaction 6, we can see it's a substitution reaction. But of course, you are allowed to faff around and say hydrolysis. Still okay. But, please, if you are asked a simple question, answer in a simple way. Don't complicate your life, or you will regret it. Hey. Let's go on, guys. The next one says, it says now draw the structural formula of the main product of reaction 5. Okay? And write down its IUPAC name. Now let's look at reaction 5. Reaction 5 is basically going to be adding water. It's hydration to this thing. Okay? Hydration. Now remember, from here we lost this chlorine and we're going to lose one of the hydrogens. But most likely it's not going to be hydrogens far away. We will lose one of the hydrogens in the next carbon. So it can be either this guy or this guy. But we're not going to lose a chlorine and a hydrogen on the same carbon. If we lose a chlorine on this on this carbon, somebody needs to die. Sorry guys, just a moment. Okay guys, there was an insect here which I know has bitten me before. So I wanted to take care of it. See, the black widow spiders are dangerous. I don't know how it got here. And I won't let it do it again. It gave me hell. Anyway, let's move on. So we were trying to get a structural formula of the main product. Okay. Remember, this is an addition reaction, so we follow Markovnikov's rule. Now the question is, where will this double bond be on this molecule? The double bond is on the first 2 carbons. So if we have the double bond on the first 2 carbons, so essentially compound C is going to be something like this: 1, 2, 3, 4, 5, right? Then of course we've got 2 hydrogens there, 1 hydrogen there, and then we've got something like this. It's C5, 1, 2, 3, 4, 5, and then H10, 2, 3, 5, plus another 5, 10, okay? So when we add water, we know water is going to ionize into hydrogen and OH minus, okay? So Markovnikov says this OH group will go to the carbon. Remember, you always look at the 2 carbons participating in the double bond. You don't look elsewhere because you're going to burn. Now of these 2, which one has the most hydrogens is the first one. This is where the hydrogen will add. And then the one that is, has less hydrogens will take that OH minus. All right. So basically, what do we end up with? We end up with a structure like CH3, because we're told here we must do a structural formula. And then here we're going to have CH, and then here we've got an OH, and then we've got 1, 2, 3, 4, 5. So the others pretty stay the same. Okay, so this is the structure that you are expected to put down in your answer book. So the rest was just your thought process to decide where the stuff goes, okay? So it's going to form a secondary alcohol. And then now we're told we must give it an IUPAC name. So this is basically a pentane 2-O, okay? Because it's on the second carbon. You always prioritize the functional group. So, which I don't understand why in the case of haloalkanes that is disrespected, even though haloalkanes by definition actually do have a functional group. Anyway, let's leave the stories to those who can tell it. So basically here the position of the OH and the parent chain and the IUPAC name, I think is where the 3 marks come from. Let's finish up this thing now. It says now write down the type of addition. Now this is where they like to just mess around. You can't say the type and then name the type again. Just say the specific name. That makes it a bit better. Anyway, addition reaction represented by reaction 3. So we can see here this is hydrohalogenation. So that's the name that they want. It's a specific name. So 4.4. This is hydrohalogenation. All right, not a big deal, easy one. It says now write down the number of the reaction that would take place if the relevant organic compound was heated strongly in the presence of concentrated alcoholic potassium hydroxide. But what do you notice here? This guy needs to be concentrated. Now let's look which reaction would, okay, this is a question of would take place if the relevant organic compound was heated strongly in the presence of concentrated alcoholic potassium hydroxide. Once we concentrate, we look for an elimination reaction, okay? So remember, reaction 6, if we use a dilute base, we do a substitution. But if we used a concentrated strong base, we would actually do an elimination reaction. So this is reaction 6. Because it is hydrolysis, but if we used a concentrated strong base there, we would essentially have an elimination reaction, technically. All right, so that is reaction 6. So if you wrote 6, you are good to go. All right, guys, we made it because I wanted us to then enjoy these new questions for your grade 12 in term 2, because most of the work we've just done so far was term 1. So let's do question 6 quickly. Sorry, question 5. Okay, so we're doing question 5 now, so we're going to try and speed up. So we're told you study the following chemical equation. I cannot overly emphasize why you need to inspect. So this is carbon monoxide gas reacting with nitrogen dioxide gas. Okay, carbon monoxide is colorless, nitrogen dioxide gas is brown. Okay, then we're going to make carbon dioxide, which is sort of like a milky gas that's colorless in a way. So we're going to form ourselves a carbon dioxide gas and nitrogen monoxide gas. Wait a minute. So what is going on here? We're told here also that the forward reaction, because remember delta H is always for the forward reaction unless otherwise stated. If they just write delta H, it's always for the forward reaction. Great, so we can tell that this is an exothermic reaction. So this means heat is eliminated here. Okay, meaning this forward reaction is basically exothermic. Now it says here, Use the above equation and draw a potential energy diagram. Okay. Label the specific reactants and products. See, they want the specific reactants and products as well as the activation energy and the heat of the reaction. So this is a very easy question. So 5.1, we can deal with it this way. So we draw axis here. Slanted. Much better. Okay, so we know that here we talk about of potential energy on the y-axis. Then of course it's always in kilojoules per mole. Okay, always state the SI unit for that. And then here we just call it the reaction coordinate. Okay, so please remember those things. And then now what do we do? Well, what we do is stuff like this. We know this is an exothermic reaction, so the energy of the reactants is always higher than the energy of the products. Okay, so we know that here we're going to go to the top because we're going to go and approach our activation energy, and then we come back down. All right, and then we're going to have our products. Great, so this is what we've got. And then we were told to label the individuals. So it's going to be CO2 plus NO2. Of course, this is a gas. And then we're going to have here carbon dioxide plus nitrogen monoxide gas. All right, so we've labeled the specific stuff that they wanted. Now the question was the delta H. Remember, delta H is the difference between the energy of the reactants and the energy of our products. Of course, here you can break this line to show that it does not really exist, but it's something that you are using to draw your conclusions. All right, so we can say this is the delta H, which we were given here, it's minus 60. Okay, of course, you know that it is in kilojoules per mole. And then now we have another stuff to handle. If we draw another line here, because that line doesn't exist, but it helps us to work out the activation energy. So we can just label it here that this is the activation energy. Because we don't have values, so we'll just keep it like that. So what were we asked? Label the specific reactants and products. Done. And then as well as the activation energy, we've labeled it, and the heat of the reaction, we've labeled it. So we have our 4 marks in the bag. Okay, so that is good. So that is good. So we've done it. And then let's move on. It says now define the term catalyst. Again, guys, easy stuff here. No need to be losing marks here. We can say it's a substance that speeds up a reaction by lowering activation energy. Without itself taking part in the reaction. Again, you've got nicer and more concise definitions. Please consult them if this one is too difficult, but I'm trying to push you into using your own knowledge, your own thought process to make sure you arrive at the answers that are needed from you. So 5.3. What is the next question? It says the following table shows two catalysts that can be used for the reaction, for this reaction, and their corresponding activation energies. So platinum, the activation energy is 70. The osmium, the activation energy is 104. So the lower the activation energy by a particular catalyst, the better it is for a particular reaction, because we always want the lowest possible activation energy. So now it says which catalyst, platinum or osmium, will be more effective for this reaction, and then of course use the collision theory to explain the answer. So again, this question is forever there, so you cannot escape it. So 5.3, it's going to be platinum. And the reason is it has the lowest activation energy. Okay, the lowest activation energy, and hence more molecules will have sufficient more molecules will have sufficient average kinetic energy to form more effective collisions. Hence, the reaction rate, or more effective collisions per unit time, and hence the reaction rate will be higher. Great, so that is the story. So you try your best to make sure all the right scientific terms are used in the right context. So we'll just say it has the lowest activation energy, as we can see there. Hence, more molecules will have sufficient average kinetic energy to form more effective collisions per unit time. Hence, the reaction rate will be higher. Simple as that. So you try and make your argument as great as possible, and you score your marks. Okay, guys, let us go on. Question 6. Now, question 6 says, start on a new page. A student investigates the reaction rate between magnesium and sulfuric acid. Okay. Now, the balanced equation for the reaction that takes place is, as I said, always investigate in these things. What is magnesium here? It's in solid form. If it is in solid form, what would be the oxidation number? 0. It's a natural state. But look at magnesium in this instance here. magnesium is basically 2 plus because the sulfate ion is a 2 minus. So the sulfate ion is a 2 minus. And as you can see, the sulfate ion here is also a 2 minus. So it is a spectator ion here. It's not taking part in this reaction per se. But what is happening is between magnesium and hydrogen here. Well. Let's look at the hydrogen here. The hydrogen is basically 2 plus here. And then here it's 0. So the hydrogen has actually decreased in its oxidation number. So this is again a redox reaction. So reduction and oxidation is taking place. Okay, with the sulfate ion being the spectator ion. Okay, all right, okay. So again, when you react a metal and an acid, you always form some salt and hydrogen gas. Usually the main reason for the reaction being the attempt to produce the hydrogen gas, most likely. But if you want this salt, you can easily get it this way as well in the lab. Now we're told here, the student repeats the experiment a few times with different concentrations of sulfuric acid. Okay, now all other variables are kept constant. Again, this is a question on reaction rate, so you're getting 2 questions here technically. Anyway, the results are recorded in the table below. Concentration of sulfuric acid 0.4 mole per decimeter cubed. The reaction rate is 4.2, and you can see here, as we increase the concentration of the used sulfuric acid, and so does the reaction rate, it increases. Not a problem. So it's a linear relationship. It's a straight line through the origin. It's a direct proportionality, if you were to ask me. Now formulate an investigative question for this investigation. Okay. Well, if you want to investigate, it's as if you don't know, but you already know. Okay, 6.1. So we can just say, what is the influence of a change in concentration? What is the influence of a change in concentration to the rate of a reaction? Okay, easy stuff, because all you want, what will be changing? The concentration of the sulfuric acid to what? The particular given reaction. So keep it simple, keep it concise. So 6.2. Question says, write down one variable that must be kept constant. Obviously, there's a lot here. There's a lot we can think about. We can think about the state of division of magnesium. Okay, that's one. But name one, don't list them. And then the other one that we would want to keep constant here is basically the temperature. The temperature, because we don't want it to have an influence here. So what else can we modify here? Oh, maybe the amount of magnesium. Okay, we want to keep it constant. Yeah, you can name any of the 3, so that would be fine, but they only wanted 1, so don't list all 3. What will be the effect on the reaction rate if lumps, you see, of magnesium are used instead of powdered? That is the state of division. Write only increase, decrease, or remain the same. Okay, Obviously, if we use lumps instead of powder, lumps have a smaller surface area than powder, so the reaction rate will decrease. So 6.3 will just write decrease. Alright, so it says use the collision theory. Oh, doc, I'm tired of this question now. How long have we been using this collision theory now? To explain the answer in 6.3. Doc, can you spare me the rod on this one? Well, we know that magnesium rod MG rod will have a smaller surface area for its particles to collide with particles of the acid. All right, hence the reaction rate will be low. Okay, let's just say lower. So the magnesium rod will have a smaller surface area for its particles, not just particle, to collide effectively with the particles of the acid. Hence, the reaction rate will be lower. Of course, you don't want to sink too much here. You want to keep it to some sort of a minimum, you know, we don't want you to sing too much. When there is a way of singing less, you sing less. Okay, let's do it. Now 6.5 says, what will be the effect on the rate of the reaction if the temperature increases from 20 degrees Celsius to 30 degrees Celsius? Write only increase, decrease, or remain the same. It obviously will increase. Okay, the temperature will increase the reaction rate. Simple as that. Okay, so we've got a situation now. An experiment was conducted to investigate the reaction rate between excess calcium carbonate. So what does that mean? If we have excess calcium carbonate, it means this is the rate limiting reagent. It's an RLR, okay? And then we've got nitric acid here, which is completely expunged, it seems. And then we've got now calcium nitrate, salt, water, and carbon dioxide. Okay, then of course, what would be the pH of this one? Oh, doc, if it is the calcium carbonate in excess, it already tells us that this salt is basic. And we know it. When you take a weak base, you react it. Oh no, wait a minute, I'm lying. I'm seriously lying. It's a strong acid against a weak base. So this is a strong salt. So most likely going to be acidic than basic. And as you can see, anything that releases carbon dioxide will actually form an acid somehow. All right. Okay. All right. So please think about these things. They are very important. Okay. But the issue now is the fact that the calcium carbonate is in excess, meaning a portion of this will neutralize this acid, okay, completely, whereas a remainder will be that of the calcium carbonate. So as a result, the pH should be low, eh? Yeah, now should be high because the base is in excess. So there will be more hydroxide ions than, yeah, okay, great. So sometimes be very careful. When there's not a complete neutralization of one by the other, the salt is not going to tell us the pH, but whatever is in excess determines the pH of the final solution. Alright, so there we are. So you already know how these things work, okay? I'm not going to explain. Everything is balanced. So here we got here 4.5 grams lump of calcium carbonate, and then it's bumped into some 200 centimeter cubed of a 0.3 mole per decimeter cubed of nitric acid at 25 degrees Celsius. Here we're using a higher volume of the same concentration. So what matters is the concentration. Volume does not really matter in terms of the acid, okay? Now it says calculate the volume of carbon dioxide produced at STP in flask A. Alright, so 6.6. Now we're doing some serious stuff here. 6.6, we want to know the volume of carbon dioxide produced. So here we cannot use what goes in excess, the calcium carbonate, because it's not going to help us a lot. But we have to use what is used up completely, which is the acid. And now we have the volume, we have the concentration, we can find the number of moles. All right. Yes. So basically, what do we know? We know that the number of moles of carbon dioxide produced is equal to, remember now it's a 1:2 ratio, is going to be equal to 2 moles of HNO3 used, okay? Because it's a 2:1 ratio. It has to be half, man. What am I doing? Damn it, man. It's gonna be half. Okay, so these are some of the most important statements you can ever write for yourself, guys, because the molar ratios in the chemical reaction help you to determine the direction. So this then is equal to 0.5 into the number of moles is always volume multiplied by concentration. So this is basically going to be 0.2 multiplied by 0.3. Why do I have 0.2? It's a conversion of 200 centimeter cubed to a decimeter cubed. So we say 200 divided by 1 squared, we get a 0.2. Okay. So what do we get? 0.2 times 0.3 times 0.5. So I'm getting a 0.03 mole. Okay. So we've got 0.3 moles of carbon dioxide. But now we are interested in the volume at STP. That means we're going to use our general gas equation. We can say then, we know that PV is equal to nRT. Is it not? Yes, that is the story. Which implies standard pressure is 1 atmospheric pressure. Yeah, let's go for that little thingy. I don't remember that thing now. The standard pressure here is in pascals. Here. And we always use this one in kilopascals. But here, for us to be safe, because if we're using this formula, so it means we're going to use pascals, ne? We're not going to use kilopascals. So technically our pressure is going to be 1,013 times 10 to the 5 into the volume, which is what we want, equals the number of moles is 0.03. The general gas constant, do we have it here? I'd be dead if they didn't put it here, because I don't remember it by heart, but words. Yo, I don't. And it doesn't look like it's here. Words. How do we remember that thing? Is it 8,3 something? I think it's 8, some change into 8, is it 2, 3? I don't remember. And then of course the standard temperature is 273 kelvins, so it's 273. Let me just double check our general guess thingies. And then of course if we don't get this value, we are dead. Okay, let me just double check this thing quick. Okay guys, I found it. I cannot believe in your information sheets this is not given. So it's 8,31. So this is 8,31. Let me just check. Yeah, joules per Kelvin per mole. So I don't know why they did not include it, but yeah, anyway, that is what it is. So therefore our volume is going to be 0,03 into 8,31 into 273. All of that divide by 1,013 times 10 to the exponent 5. And this will give us the volume in decimeter cubed. Yes, 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 because the kelvins will take care of each other. Nice and easy. Because this is per Kelvin, this is times Kelvin, so they go out. So let's do it. So we've got 0,03 into 8,31 into 273 divided by 1,013 times 10 to the 5. All right, so let's see. I'm getting a 6,7. Say minimum of 2 decimal places, 72 times 10 to the minus 4 decimeter cubed. Oh, wait a minute. Konje, is this thing in decimeter cubed? Yeah, at STP is in decimeter cubed per mole. My worry is, do I use pascals or kilopascals? That's where my little trouble is. Yo, bafethi nizozodliwa into encinci kanje. Ayisuka, mayingandiqheli kabi. Theni nizoqhelwa into encinci ngoku? Ewen, unketsa njwali. Because I think this is in meter cubed. It's not in decimeter cubed. I think this is in meter cubed. Anyway, anyhow, let's leave it alone. Because what is this guess we are dealing with here? It's not an ideal guess. So it's most likely to be like that. But I think this is in meter cubed. I think so. I don't think it's decimeter cubed. I think it's meter cubed. Yeah. And then maybe the trick is that we need to convert that to decimeter cubed. But anyway, guys, it's a very simple calculation. I could be wrong. It's not per decimeter cubed, but it's decimeter cubed per mole. Okay, so that is what I can see here we can do. Yeah. That is it. Let's just forget other things. They are not going to be useful. So here you've got a formula. We do a substitution and then answer. Standard 3 marks. Oh, there's 4 marks here. So basically, the 4th mark is technically getting that number of moles. Yeah. Alright, so it says use the answer in question 6.6 to calculate the rate of reaction in flask A. So we want the rate of reaction in flask A. Okay. I think at this point I'm feeling a bit fried. I thought I was going to be doing 2 questions only. Now I'm stuck with this thing. Okay, for the first 20 seconds. Alright, not a problem. So we know that we produced this volume. What is the story again? Yeah, we want this one in decimeter cubed times second. Per second, sorry. So this is a very easy calculation here. So 6.7. We know that the reaction rate is going to be the change in volume over the change in time. The change in volume is effectively what we produced is 6,72 times 10 to the minus 4 all over 20. Okay. So 6,72 to the exponent minus 4 divided by 20. We're getting here a 3,36 times 10 to the minus 5 decimeter cubed per second. Okay, not a problem. Very simple. Very simple calculation here. So formula, substitution, answer, easy stuff. Now how will the rate of the reaction in flask B compare to that in flask A? Choose greater than, less than, or equal to. It has to be equal to. Why? Because we're using the same concentration. The volume doesn't matter. The volume doesn't matter. What matters is the concentration. So basically 6.8 is that it will be equal to. Okay guys, I took forever here. I don't like what happened. We ended up taking longer than I was planning to take. So let's get to chemical equilibrium. So question 7. So now we're told gas A2B is introduced into a flask, which is then sealed and allowed to reach dynamic equilibrium at a certain temperature. Now, the balanced chemical equation is this one. So we've been given stuff that we need. So not a big deal. Now it says the graph below shows the change in the rates of the forward and reverse reactions with time. Okay, great stuff. So the solid line, okay, they're telling you the solid line represents the reverse reaction. Sorry, in any case, even if they didn't tell you this is the reverse, if you were given this graph and you have to decide which one is which, you always start at some higher rate for the forward reaction, right? And then it goes up, and then the reverse reaction catches up along the way. Is it not? Yeah, but let's see. Am I saying something that makes sense? No. Now, for this to be the reverse makes no sense to me. Because how can this one? How can this one be the reverse? Oh yeah. Let's just assume that at time t0, the reaction is already occurring here. It makes sense that this one should be the forward reaction, because the forward reaction decreases over time while the reverse reaction catches up over time. So be able to interpret this thing even if you're not given a clue like this one. Okay, so let's see. We can see that here between T60 and T120 we've reached equilibrium. And then something happens at T120. Okay, so something happens at T120. And then it also happens again at T180. And stuff happens again at T240 seconds. All right, so let's explore what is going on here. Now it says define the term dynamic equilibrium. I think at this point I'm tired of doing definitions for you guys, but hey, oh, doch, will you stop? Will you stop touching things? Yeah, this thing is going to drive me nuts. Anyway, forgive me for the choice of words there. We can say dynamic equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. That's what it is. Dynamic in the sense that the forward reaction is equal to the reverse reaction. That's it. Now, at time T120, the volume, okay, that they're leading us. Of course, we needed to explore what could have happened. So they're telling us that the volume of the container is decreased, which leads to an increase in pressure. Obviously, if you see these ones immediately going up like that, they first, at T20, they sharply rise together before the other one continues to rise on its own. So that initial rise tells us that pressure must have been manipulated, okay, for both reactions to just quickly rise at first, and then the other one is more favored than the other because of some differences in how pressure will affect the system. Look at this this equation. There's only two particles here, basically, to the right, to the left, versus 3 particles of gas molecules to the right. So if you increase pressure, we favor the reverse reaction. So it makes sense. It makes sense. Okay, so our 7.2.1. The question says now, the graph shows that T120, both the forward and the reverse reactions initially and immediately increase at the same rate. Explain this observation. Well, this is very easy. We can see that an increase in pressure will initially increase the concentrations of both products, it's just of both reactants and products. Okay, so an increase in pressure will effectively increase the concentrations of both reactants and products. Therefore, you can say hence the initial sharp rise in the reaction rates of forward, and reverse reactions. Okay, yeah, my writing is starting to do its thing of fading, but in any case, you just explain what happened. Technically, it is an increase in the concentrations of both. So if you increase the concentration of the of the products, what happens? The reverse reaction will be much sharper, as well as would be the case when you increase the concentration of the reactants. It will be, for that moment. Of course, these are unequal in the long run, but instantly they more or less look the same. Okay, that's easy, 2 marks, no issues there. Which reaction is favored between T120 and T150? Now, between T120 and T150, we can see that it's the reverse reaction that is favored, because the one that is above the other is the one that's favored. So it is the reverse reaction. Yeah. So 7.2.2, it is the reverse. Okay, great. Not a big deal. So they're asking a question using Le Chatelier's principle. Explain the answer in question 7.2.2. Well, we know that here an increase in pressure will favor the reaction that lowers the number of gas molecules in the system. Therefore, the reverse reaction is favored, as it results in fewer. How do you write fewer? Gas particles. You can use the word molecules or particles, it's up to you. You can see here there's 2 against 3. So basically that is what is happening. Le Chatelier's principle, you don't really have to mention the person's name, because all you are saying, you are reversing a disturbance basically. That's the essence of Le Chatelier's principle. So you can do it by mentioning him, or you can just do it by taking what is the essence of, that stuff right there. So 7.3 says, at time 180 is the temperature, or at time 180 seconds, the temperature of the container is decreased. As we can see here, they initially both decrease. But you can see that the reverse reaction is affected more than the forward reaction, because as you can see here, the forward reaction is still there, while the reverse reaction now is going to play catch up at the end. Okay, so as we inspect we know that of course they both decrease, because if we decrease the temperature, both the rate of the forward and the reverse reaction gets affected, but depending on which one is endothermic and exothermic. If a decrease in temperature favors the forward reaction, it means the forward reaction is exothermic. Okay, all right, so it says now, is the forward reaction exothermic or endothermic? The answer is exothermic. Okay, you can say a decrease in temperature favors an exothermic reaction. Okay, that's what it does. And we can see here the forward reaction was favored to some extent by that decrease in temperature. So we are done here. We don't need to say too much. We are sorted here. Now what change was made at T24T? Great, we can see here again both the forward and the reverse reactions increased. Okay, so here which one doesn't favor the reverse or the forward reaction but just increases both? It's a catalyst, is it not? Most definitely. It's most likely, let me not say most definitely, it's most likely a catalyst. Okay, we must have added a catalyst because it does not discriminate between the two reactions. It doesn't favor the other one more than the other. It favors both equally. Great. Now it says, how does the concentration of this gas, which is A2B, which is the reactant in our equation, change between T230 and 250? As we can see here, from 240, in fact, look at 230 would be somewhere here, right? And then 250 probably somewhere there. Now, what happens here? Look, if we're in equilibrium, it means the concentrations of products and reactants are constant, okay? And then here we're rising both the forward and the reverse reactions by the same rate. So that means the concentration stays constant. And then we reach equilibrium, we still stay constant. So it remains the same. Okay? Explain the answer. Well, we know that the rate of the reverse and the forward reactions are equal. That's what I can say. That's it. That's why they will stay the same. Because when we're in dynamic equilibrium, you can say the system is in dynamic equilibrium even. That already tells you that the concentrations will be the same, meaning they stay constant. You can even put it what would try to throw you off is this catalyst addition, but it doesn't affect the concentrations per se, but it just affects the rate at which we attain those concentrations. Here's the stuff. Yo, guys, these people, why are they asking so much now? What will the effect on the equilibrium constant? Now, what affects the equilibrium constant is only temperature. You should know that. Only temperature affects the equilibrium constant. Other things do not. It is specific for a particular temperature. An increase in pressure, so 7.6.1, it will have no effect. Okay? 7.6.2. The decrease in temperature at T180. Now, if we decrease the temperature at T180, what happens? Remember, we favored the products over the reactants. Okay, so if we favor the products, as we can see there, it means, remember, Kc is the concentrations of products over concentrations of reactants. So now if we increase the numerator, what happens? We essentially are increasing the value of Kc, so it should increase. Okay, definitely, because at T180, the forward reaction is above the reverse reaction to suggest that it is favored, okay, until they become in dynamic equilibrium again. Not a problem, not a problem. So let's move on. Is there any more? Yeah, there's more. Yeah, when? The big one, 7.7. Now, initially, 5 moles of gas A2B. So let's write this thing down. A2B goes into, we need that equation now, 2 of gas A plus just a diatomic form of B. Okay. All right. Okay, so there is 2 here. Sorry. Not a problem. So we've sorted that. And then, of course, we are told initially. What did we put in? So this is going to be a KC calculation. We put in 5,1 moles of gas A2B. And of course, initially there will be nothing of their products. And then we are told the flask is then sealed and kept at a constant temperature. Now the gas A2B decomposes as shown, okay? They are repeating it. When dynamic chemical equilibrium is reached, 3,6 mole of A2 remained in the flask, okay? So this means we don't know what is the change here. The change is usually what we can say used or produced. And then now at equilibrium, what are we talking about now? We are saying there were how many? Sorry, I didn't write my equation correctly. 2A2, ne? Yeah. So now we're told you there's 3,6 moles here at equilibrium for this one. Now because this is a 2:1 ratio, so we just take 3,6 and divide it by half. Sorry, by 2. Sorry, 3,6 divided by 2 to get the number of moles that should be present of gas B2. Okay, because it's a 2:1, so just half that. That should be the one. But then, if this is what we get at equilibrium, it means this is what we produced, because there was nothing initially. Okay, now on this part, this is when we can cross over to the other side. So this is 2:2, so we actually used up 3,6. Then now the difference between 5,1 minus 3,6 will give us the equilibrium concentration, which is 1,5, right? You just take the difference there. Then now we want the equilibrium concentration of these ones, but now we have a problem. We don't know the volume of this thing is, but they're already telling us that the equilibrium concentration of gas A2 is 1,2 mole per decimeter cubed, 1,2. So if it is 1,2, we need to perform a calculation of finding the volume. So we know that, well, the concentration of A2 gas is going to be number of moles over volume, which implies that we've got 1,2 equals the number of moles is 3,6 over volume. Therefore, the volume here is going to be 3,6 divided by 1,2. It gives us 3 decimeter cubed. So this is very important, because without it we cannot do anything. Now we can finally do the concentrations here. So we're going to have 1,5 over 3 which is basically 0.5. Ne? Yeah. And then that one is sorted, so 1.8 divided by 3 is what? Is 0.6. Okay, so this is mole per decimeter cubed, of course. Now that we are sorted, what do we do now? It says calculate the equilibrium constant Kc. We can then say then Kc is going to be the concentration of A2 squared into the concentration of B2. It's always products over reactants. Concentration of A2B squared. Now we substitute. So we've got here 1.2 squared into 0.6 over 0.5 squared. So let's get our Kc. So what I'm getting here, I'm getting a 3.46 to 2 decimal places. Remember, we're told minimum, so we're just going to keep it to the minimum. Okay guys, so that is the story, so we can just move on. So basically this 7 marks in our opinion, okay, in my opinion, it's a mark for finding that volume, because without it, life becomes a bit difficult, okay? And then of course, finding this number of moles here is key, and essentially finding the number of moles at equilibrium for that gas is another mark. So how many marks have we got here? 1, 2, 3. And then of course these concentrations were not given to us, we had to calculate them. So we've got how many marks now? 5 marks. Okay, yeah, doch, this is terrible. And then substitution answer is fine. It's fine. Should have been 8 marks, because I still feel that this guy is worth a mark for determining that guy. So it's fine, not a big deal. 7 marks in the bag. So these are some of the questions that will always horrify your experience of chemistry. But remember, if you stick to molar calculations in your stoichiometric calculations, if you focus on the number of moles, you will not get it wrong. Yes, it may be the longest route sometimes, but you won't get it wrong. Anyway, let's move on, guys. I don't have time to waste here. Let's get to question 8. I wonder what's the time, eh? I'm having fun here, and it may be very late. Okay, so let's do question 8 quickly. So we're told Elena prepares sulfuric acid, which is H2SO4 solution with a concentration of 0.25 mole per decimeter cubed. It says now give a reason why sulfuric acid is referred to as a diprotic acid. Of course, the word is self-explanatory. So it is because it donates 2 moles of H plus ions. Oh, okay. You can say it liberates 2 moles of hydrogen plus ions, or it can donate 2 moles of H plus ions whatsoever. It doesn't matter. Or it can donate 2 protons, whatever. Dissociate into 2, whatever. Yeah, we just want to keep it moving now. We don't want to complicate our lives. Determine the pH of the solution. Of course, we know that the concentration of the hydrogen plus ions is going to be 2 times the concentration of the sulfuric acid because it dissociates into 2 of them. So this is going to be 2 into 0.25. That is just 0.5 mole per decimeter cubed. Alright, so we can say this implies that pH, in fact we don't say implies, we know that pH is equal to minus the log, the concentration of the hydrogen plus ions, which is minus log 0.5. So minus log 0.5 is basically 0.30. No, it doesn't have units. So they said minimum 2 decimal places. Don't forget that. So this is a nice calculation. 4 marks. Of course, determining the concentration of that story is important. And honestly, for me, that is also important. And this is important, and the answer, I don't know, whatever. Usually, a formula can get a mark or whatever. It just doesn't matter. At the end of the day, the 4 marks are in the bag. Let's move on. 8.1.3 says, the learner takes 20 centimeter cubed of the solution and dilutes it to a solution with a concentration of 0.1 mole per decimeter cubed. It says now calculate the volume of water that was added to the initial 20 centimeter cubed. So this question is a silly question. It can hurt you if you don't remember. Now look, we took a particular concentration and changed it to another. What is constant here is the number of moles, because the only difference is the volumes here. So we know that the number of moles in the first instance is going to be the number of moles in the final solution, right? Yeah, that is the story. But then how do we define number of moles? It's concentration multiplied by the volume. Okay. And then this implies now the first concentration was 0.25. Right. Into the volume we're given that it is 20 centimeter cubed. So at this point you can leave the 20 because you have centimeter cubed on either side of the equation where you have only one term, so they will cancel out, so you don't have to change them. Now the second concentration that we're given is 0.1 into V2, which is what we want. Therefore, V2 is going to give us the total volume, right? It's going to be 0.25 into 20 divided by 0.1. So this gives us 50 centimeter cubed. Okay? Because remember, we used centimeter cubed here, so we keep it as that. We can say therefore a volume of 50 minus 20 centimeter cubed, which is equal to 30 centimeter cubed, was added. There's plenty of ways you can do this, but in essence, they wanted to find out how much must we have added. Remember, this is the total volume of the second solution. So what did we add? We added just 30 centimeter cubed. So you can change it to decimeter cubed if you want. This calculation is a bit fair, so it doesn't dictate what must be added or not added. All right, so let's do 8.2. What is that? 8.2. I'm using the same canvas as I was using for other questions. So you see, it's making me look crazy now because my script is dirty. Anyway, I'm not the cleanest person ever. Of note, so leave me alone. I like to use the same canvas and just modify stuff so that I work easy. I make my life a lot easier. But you can't do that, eh? Every question must have a new page for you, so you're not gonna do like me. Okay, now it says a few crystals of ammonium chloride are added in water in a test tube and the pH of the solution is less than 7. Of course, because we know that this is an acidic salt. So it says now explain with the aid of a balanced equation why the pH is less than 7. So this is important. We know that if we take ammonium chloride, so this is NH4Cl plus H2O. So this one acts as an acid and this one as a base, right? Right. So what happens here? Let me try to think. What am I saying to you now, guys? Am I lying or am I telling the truth? Yes, it doesn't matter. So, let me think again. So we've got H2O here. So who does what to who? You know, who does what to who? This one looks a bit complicated because it's one of those difficult ones to actually write out nicely, you know. But all we know is that this guy is going to protolyze this dude. Of course, you don't do this, okay? This guy is going to protolyze the water because water acts as a base here. So all we're going to end up with is H3O plus because water will accept a hydrogen or a proton. And then now what we end up with here is ammonia. Okay? Which is a weak base, right? And chlorine. Okay, so for me, chlorine is just going to be left out in the cold. Okay, chlorine is going to be chucked out in the cold. So what happens here is that this is a weak base, this is a strong acid. So as a result of this guy, so we can say the solution yields the H3O plus ions, which are a strong acid. Then the pH of the end solution, ion, what is that? Of the end solution will be acidic. Okay, so that is the story right there. That is the story right there. So certain things are strange, okay? Certain things are strange. In fact, that oxonium ion may actually pick up the chlorine, but you want to show what is going on. Great stuff. No problems. We just move on. But double check this thing. I may be lying to you sweetly. Sometimes I don't remember these things, guys. Hey, tazenza kudala kaloku ezinto, so ingqondo yami iphithizela zezinye izinto ngoku. So if I lie to you, you will find yourself a solution somewhere. Please tread carefully in my videos, okay? Because I tend to make errors in my explanations and I don't hear myself do those errors. So, of course, I don't have time to watch the entire video before I post. I only realize when it's already through. So, yeah. If I had someone to give the video to moderate it for me, it would be nice. But I don't. And I'm not even a guy who likes to edit videos. So, just throw it there. You will find out what you will find out. But I'm sure most of the things are going to be correct. Most of the things are going to be relevant, but some of the things may not. But again, those are teaching points in a way. It's an indirect way of, emphasizing on some of the mistakes that are commonly made by everyone so that you guard against them in your exams. So it's not all too bad when I make a mistake, but it helps you to not make that same mistake. Let's move on. So we sorted it. And then now let's go on here. It says the hydrogen sulfate, okay, ion, so this is a 1 minus, can act as both an acid and a base. So we know that that's an ampholyte. So it reacts with water according to the following balanced equation. Fine. Write down one word for a substance that can act as both an acid and a base. Wow. We call it an ampholyte. Okay? Dazi-ke ngokwenzeka ntoni apha. Ha ke tsebe hore ho etsahalang jwale. We call it an ampholyte. Ho etsahala dintho jwale. Wenhlakalani. Inhlakala shilo sa ku nandzika. A ni swi tivi. Hi ku ri hi xilo sini leswi. Yeah, when you're not a South African if you cannot damage a few lines, in these languages of South Africa. I'm only missing Ndebele, Afrikaans, and Tshivenda. If I can know those ones, I would call myself a complete South African. Right now, I'm a limping South African. All right. 8.3.2 says, write down the formulae of two bases in the above reaction. So 8.3.2. We can already tell that in this reaction right here, this is the reaction we're talking about. This is a base because it accepts a hydrogen from that hydrogen sulfate. And this is also a conjugate base of this conjugate acid as a result. And this is a conjugate acid for this conjugate base. All right. Okay. All right. So the basis now is basically water. They said formulae. And the sulfate ion. Okay. So those are the two bases. Easy stuff. So 8.4. So you'll be told now, time up, guys. Wrap up your nonsense. But because I'm taking time to explain a thing or two for you guys to benefit a little bit, although I may confuse you at some point. One of you guys told me that I confused them. Well. If you find yourself getting confused, remember, there's plenty other channels that actually do more or less the similar papers that I have done. So you may go there to clear your head a bit, all right? My intentions of allowing those confusions to come in, I'm trying to display to you the thought process that you are expected to go through as you answer certain questions, because sometimes your first answer is not the correct answer. But you see, as I go through some of the gymnastics that you have to go through and be able to perform effortlessly, this is when I bring myself back in line, and I'm trying to show you that the reason I'm not editing these videos on those parts is because I want you to see those mistakes, that anyone makes those mistakes. But how do you drive yourself back into the right path again? Because as much as they can happen, there's a way of making sure that they don't have a negative impact on you. You look into how you solve that problem. So that's why sometimes I'll say something at the beginning, but at the end, I'll say something else. And you just have to follow carefully, using your knowledge, bouncing it against your peers as well, to verify some of the things you will come across in my videos. But I'm trying to give you a most complete analysis of your question papers and how to go about answering them. Yes, I'm not perfect. I'll make mistakes along the way. Sometimes instead of putting a 3, I'll put a 2 for some weird reason. I mean, those are just lousy mistakes that you should be able to pick up and do right. Because trust me, if I do them, that means you are also more likely to do those mistakes. And you don't want to repeat them. So for me, doing everything the way it is from the ground to the very end, I think it's fair in a student who wants to have a complete package of how to deal with these issues. But of course, if you're already an A student, I mean, yeah, you're probably gonna get bored because I'm too slow for the smart ones. But I'm probably of an appropriate, speed for those who are trying to discern something and those that are struggling, which are the main target, essentially, because the ones who are struggling need to be brought up to speed, to be brought up into the light, so that they can have a fair chance to fight for survival. Anyway, guys, let's not talk nonsense. Sometimes, to just give myself a little bit of a break, I do this deliberately. Anyway, a small amount of sodium hydroxide is added to pure water at a temperature of 25 degrees Celsius. Okay, what do you know at temperature 25 degrees Celsius? Water ionizes into 2 hydrogen plus ions plus the it auto-ionizes into hydrogen plus the OH minus. So that is the property of water at this temperature. Okay, it auto-ionizes. That's what is important. Now choose between, okay, how will this affect there? Then we choose between increases, decreases, or no change. How does that affect the ionization constant of water? It does not get affected by what? Look, this at this temperature, remember, if we're keeping this temperature, the ionization constant is the same as the Kc. So basically it is not going to change, so it's no change. Okay. 8.4.2. Now the concentration of the oxonium ions. How does that change? Well. Because we're adding a base. If we're adding a base, we're increasing the OH minus ions. So essentially we are decreasing the oxonium ions. Okay, that one decreases. Great stuff. So not a problem. Elena wants to determine the percentage. Oh, it's a different question, okay? 8.5. When 8.5 says, Elena wants to determine the percentage of magnesium oxide in a health tablet, okay? She dissolves the tablet in 50 centimeter cubed of 0.8 mole per decimeter cubed hydrochloric acid solution. And we have a balanced chemical equation. For us, during our curriculum, this was the thing you had to make yourself in balance. So that's why higher grade was a bit of a situation. You needed to know how to make these equations. By just knowing the words, you needed to know the chemical formulae. Of course, by understanding how to use your periodic table the most. And some of the things using your memory, of course. Because there's not so many equations you can be given for your metric or should we say high school curriculum. All right, so let's do it. 8.5.1 says, calculate the number of moles of the acid present. That one is an easy question. By the way, we use the formula concentration is number of moles over volume, which implies we were told the concentration is 0.8 equals the number of moles which we want to find out. The volume is 50 centimeter cubed, so this is basically 0.05 decimeter cubed. So you just divide 50 by 1,000. So I don't know, I'm coughing now. Yeah, 0.05. Therefore, the number of moles of acid is basically going to be, let's just do that. Concentration of acid, volume of acid. Yeah, boom. It's going to be 0.05 into 0.8. I'm just dragging, okay? At times, you just want to play a little bit. 0.04 mole or moles, whatever. So that's the answer. So formula, substitution, answer. Remember, your answer must always have a unit of measurement. Don't forget it. If you just come up with just a number without the SI unit, you are dead, okay? So don't say they're unfair. It says, uliqelegu awukhathali, you are a hooligan in Lavin. Not quite a desirable trait in our societies. Spare that people are so individualistic and consequentialists at best. They created a very toxic society as a result of hooligans who just roam around because they can. But how it affects others, nobody assesses that. And when shit happens in our societies, then they cry that the devil is all over the place. There's no devil here. We are the devils because we let things go out of control in the name of freedom of expression, which is rubbish. Let's move on anyway. It says now, yeah, doch. Not all of the hydrochloric acid reacts. So meaning if it is in excess, it is not a rate-limiting reagent. What becomes the rate-limiting reagent here is the magnesium oxide. So meaning the magnesium oxide gets used up completely while the acid will remain. So now we're told she titrates the excess hydrochloric acid solution with a sodium hydroxide solution. So we're doing an acid-base reaction basically. Now it takes 20 centimeter cubed of, let's just use some marker here. It takes 20 centimeter cubed of 0.5 mole per decimeter cubed solution of sodium hydroxide to neutralize the excess hydrochloric acid. So meaning nothing remains after the second titration. Now the hydrochloric acid and sodium hydroxide react according to the following. Here it's a 1-to-1 ratio, so to speak. So this is the type of question that is famous and it's a killer, okay? So please practice as many of this kind as you can find, because this question is never going to let you free, okay? It's going to always terrorize you. From now on until your finals, you're going to be faced with this type of questions and they get harder, okay? Now it says here, the original mass of the tablet is this one. Is 0.96 grams. So that is that health tablet. Now calculate the percentage of the magnesium oxide in the tablet. So this is more of a grade 11 integrated into grade 12 thingy. But if you look at this question, essentially, it's more of a grade 11 question. Of course, it's a bit more complex at this point, but it's a grade 11 question. So if you're doing grade 11, you should be happy these are kinds of questions you already are familiar with, but you need to have a knowledge of some sort. Okay, 8.5.2. Now, where do we begin? First of all, we want to know the number of moles of hydrochloric acid in excess. And how we're going to know them is if we start here. We're going to start there because those number of moles are completely neutralized by the number of moles of the base. Then we will know then what was the number of moles that actually acted with the magnesium oxide. So we're going to start from the bottom up. So we're doing this now. So that's what we're going to be doing. So we're just going to be moving along. So let's start. We know that, well, we want to know the number of moles of hydrochloric acid in excess. So we will start number of moles of HCl excess is going to be equal to number of moles of NaOH that reacted, isn't it? Because that was a complete neutralization. Nice. So what is that? It's going to be concentration multiplied by volume. So this is going to be concentration of base multiplied by volume of base, which is going to be 0.5 into, this is 0.02. You convert that 20 centimeter cubed to decimeter cubed this time around. Hauna boikgethelo ntate. O hapelehile. Ba reng ba o hapeletsa. Yes. So let's do it. This is times 0.5. So we get 0.01 mole. So basically the number of moles of hydrochloric acid that were in excess is 0.01 mole. Remember we started with what? 0.04. So we were left with 0.01. Now, how much did we use against the magnesium oxide is what is the main goal. But now we want to be smart about it. We're going to try and make this as comprehensive as possible. But we're not really interested in the number of moles of hydrochloric acid per se. But we want to use them as a means to an end, you know. So if we want to make a smart argument, we're going to say, therefore, the number of moles of magnesium oxide that reacted is going to be equal to the number of moles of HCl that was used. Okay? And the number of moles of hydrochloric acid that was used is the difference between the initial minus the final, right? Which is going to be the number of moles initial minus the number of moles final. So I'm just trying to be silly here to give you something, you know, something, because this equation sometimes is something you can create. You don't need to be given a formula sheet for everything. Just know how you can use things. So do you see I'm beating two birds with one stone here? I don't want to have too many calculations here. So this is basically 0.03 mole. That is the number of moles of magnesium oxide that actually reacted. Now that is great. 0.04 minus 0.01. I have trust issues with words. So do you see this thing was becoming a little bit easier? Now that we know the number of moles of magnesium oxide, we can then work the mass because we're given the mass of the original tablet. We can say this implies, or we can say mass of magnesium hydroxide. We can say then, maybe let's do this. Let's use another word here. Let's use a but. Yebo. But that is the story. Then what? We know that the number of moles of MgO is equal to the mass of MgO over the molar mass of MgO. Of course, you don't need to write this much detail, This implies that 0.03 is equal to m over the molar mass of magnesium is basically 24 for magnesium plus oxygen, which is 16. So 24 plus 16 gives us 40. So the molar mass is 40. Therefore, the mass of magnesium that we have here is going to be 40 times 0.03, which is yeah, there is a bit of a problem. Remember, there is an issue here. Let's correct something. The molar ratio of magnesium against the HCl, you can see here is 2:1. So whatever we have to half it for the magnesium. So it's going to be half of everything that we get. Ne? Yeah. So let's start our argument properly. This is going to be half of the number of moles of HCl used, ne? Because the question here is 2:1, ne? Yeah, man, this is therefore half of the difference between the initial and the final. Into 0.04 minus 0.01. So let's adjust something. Yeah, you see, sometimes you won't see it. You see, calculation as complicated as this is always trying to take you down, okay? So a little bit of a double checking is a wonderful tool. So keep your eyes opened. Keep your eyes opened. It's easy to mess up here. It's really easy. As much as it is easy to excel. Okay, times 40. So we're getting a 0.6 grams. Okay. So do you see? We end up with some steps as much as we're trying our best to avoid too many steps. We can say therefore. Therefore what? We know that the percentage of magnesium therefore the percentage of MgO in tablet is equal to the mass of magnesium over the mass of the tablet times 100%. So the mass of magnesium is 0.6 divided by, what was that mass? They said is 0.96 times 100%. So always try to make some sort of a formula for yourself. A very simple formula. I mean, you've been doing maths for the entire 12 years, okay? So you cannot be choking on these things just because you don't have a formula. If you've been following my channel, I'm sure, without a doubt, that you should have a method by now, because I've been very, very, very attempting and tempting to give you everything that I know. Of course, not without errors, of course, because I am human too. I get consumed by excitement. And when I'm excited, I tend to be a little bit careless. When I'm worried, oh, bro, you would think I am a robot, okay? That's the end, guys. I hope you enjoyed the video and you're going to be smiling. So technically, technically this is important, and essentially this and that is important for me. First 3 marks, and then here this is the 4th mark is important, and then essentially I don't know guys, how many marks now? 1 2 3 4 5 6 7. Of course the 8th mark will depend on where you want to get the most marks, but I think the statement here is far more stronger. Sometimes these 8 marks are anywhere, so it's not really a stiff kind of a mark allocation. Please, if you find the memorandum, do check the marking guidelines and see where they decided the marks are relevant. Also discuss this with your teachers, because they try to standardize everything, but it doesn't mean you will lose marks if you didn't walk the line that they decided to walk. As long as you got to the final destination, that's the same, and your route taken was actually a legal route, then that's good. You will get all your marks. Alright guys, I've taken longer as always. I didn't want to, but I couldn't avoid it. Sometimes I just talk too much. So that's it. So please guys, you may have noticed here that this question paper has a bit of everything in it, and I've tried to expand as much as possible when necessary. So all it means, know everything that you've been taught so far, and what was in your term 1 exams is going to come back a little bit hotter and a little bit more tricky in your June exams. Same goes for those who are writing the May June exams as an upgrade. Okay, they are going to come hot. The questions that came in November are going to come hot in this May June exam, because it's a supplementary exam, so it's meant to be difficult. Okay, because the assumption is that you've been exposed exactly to how the finals look like, so you most likely are not going to be given this for free. You might as well fight for it. So please guys, make sure you know the work that was done for November 2022, even the trial papers of last year. Make sure you know everything that was in those papers. If you are lucky, you may find yourself some of those questions slightly modified, but easy to handle for you as a result. But I have plenty of videos in the channel you can look through and learn. I pretty much maintained the same, way of doing things, so that there is a bit of consistency, so that you can see if you kind of got the idea but it didn't come so clear. By the time you watch the second video, which is slightly different, you'll be probably getting the hang of the things, or the way that I'm doing things, and eventually you become the best of yourself. Okay guys, goodbye. If you spot any mistakes, please don't shy away. Just let me know so that I can confirm the acceptance of those being wrong, or I maintain if sometimes I know I'm right for some reason. So let's just keep the conversation going so that you can get the best out of your attempt in writing physics. And I think I've done enough maths, guys, like too much of it. Already this year I've done some Euclidean geometry related questions, and I've shown you exactly how you work out the most difficult and nasty type of questions that there are. But there's plenty of videos from trial papers of last year. Please revisit those, because they may come to haunt you in this June exams. Remember, June exams, they can still repeat some questions as they were when they wrote them last year. But for the May June exams, those who are upgrading, they are likely not to repeat, but they may have similar questions. That's just the idea. Okay, so please do work hard, do work smart at the same time, and make sure you know everything. The books you read in metric are too small, guys. You can't tell me that you can't remember everything in those books, because you're going to cry tears that are mixed with blood at university, because there, no one plays with you. Going to read more than one book, and each book is so thick you can't even remember what you read the first time by the time you are done with that chapter. A chapter at university is almost like half of your textbook for your metric, class. So be very careful. Don't be lazy. Those books are nothing. It's usually less text, more depictions for you to remember in your metric textbooks. So you need to understand and know everything. That's the only way you can stay safe. But if you be lazy and keep making excuses for yourself that nobody knows everything, well, you are going to find out the hard way. Anyway, guys, all the best of luck in your preparations, and I hope you are going to be smiling at the end of all the exercises that I've put forward for you and that you're going to engage in as well. As I said, there's plenty other channels for maths. I have a friend of mine, Mr. Chauke, Emmanuel. So the man does maths in a superb way. So he even knows maths beyond my level. So if you are interested in knowing maths more, you might want to stick with that dude. He will take you even across matric into tertiary. Otherwise, I'm still there. I still try to scratch the surface a bit as well. And of course, there's plenty others like the MV tutors. Those guys are superb. Please do not ignore the work that they have done for you guys. They've even done lessons, so you can learn a lot from them. And I mean, you know all the others who are already popular. So if you don't know them, then it means you're not a serious student, because those guys are too popular to not know, and they're too great to even ignore. All right. Goodbye, guys. I'll see you next time. Ciao, ciao.